Richard James will present decimal tutorial part B. In this section, we are required to write the results of two calculations correct to three significant figures. The first one is the square root of 13, which is irrational. We therefore need assistance in calculating it. We therefore consult our calculator. The square root of 13 is given as, and we are writing down every digit that is supplied by the calculator, 3.605551275. The other number is the reciprocal of 13. Another name for reciprocal is multiplicative inverse. The reciprocal of 13 is found by dividing 13 into 1, or we may find the decimal representation of 1 over 13. 1 divided by 13, and the result is the reciprocal of 13. And that turns out to be 0.076923076. The reciprocal or multiplicative inverse of 13 may be written as 13 to the power of negative 1. That is the reciprocal of 13, or we may call it the multiplicative inverse of 13. We may now go straight ahead and write the square root of 13 correct to three significant figures. Locate the third digit in order of significance by counting from the left, which is the most significant digit. So we will begin at the most significant digit that is located to the left, and we will count 3 digits. By so doing, we would have located the third digit in order of significance. So 1, 2, 3, which is that one. Check the digit that is next in order of significance, the 1. To the right, the digit is 5, which of course is greater than or equal to 5, more equal to 5. So that's what we are checking for. If the number is greater than or equal to 5, then we will add 1 to the digit in question. So we add 1 to 0. As long as it is 5 or more, we will add 1 to the digit in question, and it is 5, so we'll add 1 to the digit in question. And what happens? The other digits to the left are not affected and return as they are. No place holding 0 is necessary, as they will not affect the value of the number nor the number of significant figures in any way. Now we may write the reciprocal of 13 to 3 significant figures. Locate the third digit in order of significance by counting from the first non-zero digit from the left. So we will begin at the 1, which is the first significant digit the first non-zero digit that is located at the left. There. 2, 3. Check the digit that is next in order of significance, the one that is to the immediate right of that one. The digit is 2. 2 is less than 5. We do not add 1 to the digit in question, which is 9, and of course located in the third most significant position. So we do not add 1 to 9, and 9 returns as it is, and the other digits to the left are not affected and return as they are, like that. And again, I'm saying no placeholding 0 is necessary, as they will not affect the value of the number nor the number of significant figures in any way. And it is worth mentioning, because we will no doubt see, at least before we finish this set of tutorials, we will at least see one single case for sure, quite likely more than one though, but definitely at least a single case in which a trailing 0 contributes to the answer to the extent that it helps to maintain an approximate value of the result to the original value. But in this particular case, it is not necessary to have trailing zeros, because we are talking about decimal fractions, and we know that after the decimal point, trailing zeros do not affect the value of the number in any way. In this particular problem, as discussed before, all of the operations are at the same level, and if that is the case, execution is best done from left to right. We do not have to stick to that slavishly, because the most important thing is that everything is multiplied. We may therefore place the flat numbers together and the powers of 10 by themselves. We know that because all of these are on the same level of importance, we may begin by saying 4 times 10 to the power of 3. When we get that answer, times 2. When we get that answer, times 10 to the negative 4. But I'm saying that since all of the operations are on the same level, the order in which we perform them does not matter, as long as we operate directly as suggested inside of this problem. Therefore, what we may do is conveniently put 4 and 2 together, multiply those two, then follow up that with the multiplication of the powers of 10. 4 2's 8, and add the indices. 4 multiplied by 2 is equal to 8, and that is a breeze. No problem with that. We then need to apply the rule that when we multiply numbers that have the same base, we add the indices. Also, when we add numbers that have different signs, we subtract the smaller from the larger, and the answer will take the same sign as the larger. Good. No problem, 4 times 2 is equal to 8. When we multiply numbers that have the same base, we add the indices. The indices have different sign. When we add numbers with different sign, subtract the smaller from the larger, we get 1. And the answer will take the same sign as the larger, which is negative. So the result is negative 1. So we will have there 8 times 10 to the power of negative 1. like in a previous problem, it is good if we can see that there is an addition sign over which the multiplication operations will take precedence. And I remember, I guess, all the way over here when we have this negative sign here and the multiplication processes took precedence over this one to the extent that we perform the multiplication first. Here is no different. We have this addition sign, and I'm sure that we are right highlighting it, over which the multiplication will take precedence. And what do we know? Multiplication by 10 to the power of 2 is the same as increasing by 2 decimal places. And what we are about to do is perform the multiplication operations first, because those will take precedence over that notable addition sign that we have there. So multiplication by 10 to the power of 2 is the same as increasing by 2 decimal places, and multiplying by 10 to the power of 3 is the same as increasing by 3 decimal places. In each case, the number of decimal places in the multiplicand is smaller than the number of decimal places that we need to increase by. Additional decimal places need to be included. On the next slide, we will increase 3.7 by 2 decimal places and 2.4 by 3 decimal places. Need to increase this by 2 places of decimal, we only have 1. Need to increase this by 3 decimal places, we only have 1. So we will need zeros to make up for that deficit. We need to increase this by 2 places of decimal, 1. Include a 0 now. Now we have 2 places of decimal. And for the other one, what do we do? Going to 3, 1, 2 of them together, 2, 3. So increasing by 3 places of decimal. Add the whole numbers by aligning the digits to the right. The rightmost digit will be vertically below each other. Beginning there, the other digits are then placed to the left. The numbers are whole numbers. Therefore, the points are not necessary. Points are only necessary to depict decimal fractions, or when the form or context dictates that such is the case. Therefore, we will start with 2,400, and we have here in our statement that what do we do? Align the numbers, since they are whole numbers, align them with their rightmost digit, aligned with their rightmost digit. The rightmost digit here is this one. Therefore, when we write 370, the 0, which is the rightmost digit here, will be aligned with the rightmost digit here. And then what happens? Now distribute the other digits of the number, which is 370, towards the left. So let us do that. Put the 7, then put the 3. So put the 7, put the 3. They are vertically aligned there. And do not forget that we need to align right, the rightmost digit with the rightmost digit. Sum 0 plus 0, 0. Here 0 plus 7 is 7. Then we have 4 plus 3 is 7. And then we have what? The 2 goes back exactly as it is. We will write the answer obtained on the previous slide in standard form. When writing a number in standard form, the number is written in such a way that there is only one non-zero digit in front of or to the left of the decimal point. And that is our number. We need to have a result showing the decimal point right here. But we cannot just throw numbers down and then say that it's in the form. We need to exercise some presence of mind that if we are about to write this in standard form, which requires that only one non-zero digit is to the left of the decimal point, that we need to make an adjustment in the end, because there's no way we can write 2770 as 2.7 and that be a correct answer. No, there's an adjustment that we have to make, or we have to compensate for the adjustment that we make with the places of decimal. But before we do that, we need to know how many of them we have. So we count them. How many places? 1, 2, 3. It requires an adjustment by 3 places of decimal. The number is reduced by 3 decimal places. The number is therefore divided by 10 to the power of 3. Surely what we have here as 2.770 is less than what we have here, for sure. That means this represents a reduction or a decrease by 3 places of decimal, which would have been the case if we divided this number by 1,000 or 10 to the power of 3. So we have divided by 10 to the power of 3. Now we need to multiply by 10 to the power of 3 to recover. So we need to recover the original value of the number, and we do that by multiplying by 10 to the power of 3. So whereas to get here we had to divide this by 10 to the power of 3 or 1,000, we cannot comfortably leave the number as 2.770 without accounting for the difference. As for me, my conscience would bother me to do that. Therefore, I will have to make the adjustment in the end. And we divided by 10 to the power of 3 or 1,000. To get to this place, we need to multiply by 10 to the power of 3 in order to return to the original case. We may consider a number that initially had a digit or set of digits greater than 0 to the left or in front of the decimal point as a large number. As a rule, we may say that numbers that were initially large should be accompanied by positive powers of 10 in the end. The number of decimal places by which one number differs from the other will tell us the size of the power. So this is a large number because we have non-zero digits to the left of the decimal point. It is large. We are sure that the power will be positive. So we are sure of the sign already. In the beginning, we have decided that the sign of the power that we are going to accompany the number with, the power of 10, will be positive. because it is large, having non-zero digit to the left of the decimal point. Positive, but positive what? Is it positive 1, 2, 3, or 4? The number of decimal places will tell us whether it is 2, 3, or 4. And in this particular case, the number of decimal places by which this number differs from this is 3 decimal places. Therefore, it is a positive 3. The sign is positive because the number was initially large. The number is 3 because the difference between the two numbers is by 3 places of decimal. A 0 that traces the decimal point is not necessary in this particular case because it is not contributing to the value of the number in any way, being to the right of the decimal point. So trailing zeros after decimal point does not contribute to the number in any way. Neither are we writing to a specified number of decimal places nor significant figures. We may therefore discard that trailing 0, not having any value and not contributing to the number of decimal places or significant figure. As a matter of fact, we are not dealing with decimal places or significant figures, so that does not come in. So we eliminate that 0, and that's all there is to it. Find the square of 0.36. When squaring a number, we multiply it by itself, or we multiply 2 occurrences of that same number together. In this particular case, we will just go straight ahead and do it on our sheet of paper, or in my case, on the screen. We will do this without the use of the calculator, and by multiplying, we'll use the least significant digit in the multiplier, which is this one, to multiply the multiplicand, which is this number is the multiplicand, and we will begin here, which is at the least significant digit. So let us do our multiplication. 6 multiplied by 6 is 36. What do we do? Write 6 and carry the 3 to the next column. Then we say what? Watch those. 6 times 3. 6 times 3 is equal to 18. But we need to add this 3. 18 plus 3 is 21. Just write that down. Write down 21. That's good. What do we do next? Multiply by 3. After we have exhausted this with the multiplicand, we will go to the next slide where we will multiply by 3. When multiplying numbers with decimal fractions, we are mentioning it now, multiply them as if there is no decimal fraction. That's what we are doing. Multiplying, forgetting about the decimal fraction, forgetting about the number of decimal places. We are just multiplying. The answer will have the same number of decimal places as the total number of decimal places as the numbers that we multiply. So the answer will have, how many decimal places do we have here? 1, 2, 3, 4. So we have 4 decimal places together in the numbers that we are multiplying. The result will no doubt also have 4 places of decimal. We have multiplied by that 6. Now we will multiply by 3. We will now multiply by 3 the digit of greater significance in the number. So 3 is the digit of greater significance in the number, and that is the one that we are multiplying by now. Because of this, the first digit in the result will have place value greater than the first digit in the first result. At this stage, one may want to include a place holding 0 before multiplying the second number. 3 is the digit higher in significance than the 6. So when we multiply by this 3, the answer will begin in the position that is greater in significance than the first position that we use here. So the first position is 6, because this one is greater in significance. Then we will also have the answer down here, beginning in the position one digit greater in significance than the answer that we have here. And as a matter of fact, we may throw in a place holding 0. Then we begin to multiply. 3 6s, 18. Write 8 and carry 1. There's the one that we carry. Then what do we say? 3 3s, 9. Do not forget this one. 9 plus 1 is 10. Write the 10 down. No problem with that. Finish up by adding the two results. And do not forget, as we mentioned on the previous slide, the problem has how many decimal places? 1, 2, 3, 4. The answer should also have 4 decimal places, but we need to add those numbers. 6 plus 0 is 6. 1 plus 8 is 9. 2 plus 0 is 2. And the 1 goes back with no friend or accompanying number. And do not forget that we have 1, 2, 3, 4 places of decimal right there. Therefore, we will have how many places of decimal here? 1, 2, 3, 4. Decimal point will be right there. Good. No problem. We will write the answer obtained on the previous slide in standard form. When writing a number in standard form, the number is written in such a way, and I can imagine by now some of the math campers who are watching these videos, they are closing their eyes and they are repeating with me. When writing a number in standard form, the number is written in such a way that there is only one non-zero digit in front of or to the left of the decimal point. By now, everybody should be repeating this. And there is our number. But only one non-zero digit will be to the left of the decimal point. Presently, we do not have any. Right there. Count the number of decimal places that will represent the difference between the original number and the number written in standard form. How many? Just one. The number is increased by 1 decimal place. The number is therefore multiplied by 10. There we have it. Increased by 1 place of decimal. I am sure that we understand that this number is greater than this one. The obvious reason is that the 0 that we have here means that we do not have any whole number. in this one. But the 1 that we have here means that we have a whole number component. This one is definitely larger. Therefore, in order to get from here to here, we would have increased by 1 place, increased by 1 place of decimal, which is the same as multiplied by 10. We need to recover the original value of the number by dividing by 10 or multiplying by 10 to the negative 1. So this is an increase. We will decrease it again in order that we may have the same value that we have right here. So if we increased by multiplying by 10, we will decrease by dividing by 10 to get back to the original value, and dividing by 10 is the same as multiplying by 10 to the power of negative 1. We may consider a number that initially had no non-zero digit preceding the decimal point as a small number. As a rule, we may say that numbers that were initially small should be accompanied by negative powers of 10 in the end. The number of decimal places by which one number differs from the other will tell us the size of the power. So, small number because no non-zero digit to the left. So it is small. In the end, we are sure that small numbers will have a negative power. So we decide on the sign of the power first. And then, how large is the power? The number of decimal places by which one number differs from the other tells us the size. So the difference is by 1 decimal place. So the size is 1. Initially small number, the sign is negative. The leading 0 is not necessary in this particular case because it is not contributing to the value of the number in any way. Neither are we writing to a specified number of decimal places nor a significant figure. And even if we were, it still would not have been necessary. So, not necessary under any condition at all. We therefore eliminate it all together. Here we need to express 1/10 of 1% as a decimal. Our primary school teachers, Mrs. Peterkin, Miss Grant, and Miss Dobson, those teachers I can remember from primary school, our primary school teachers told us that of is indicative of multiplication. So if we need to express 1/10 of 1%, it means 1/10 multiplied by 1%. Of is indicative of multiplication. Everyone knows that a percentage is a fraction whose denominator is 100. Therefore, 1% is equal to 1 over 100. So, 1/10 multiplied by 1 over 100. 1/10 of 100. Multiply the numerators. 1 multiplied by 1 is equal to 1. And then multiply the denominators. 10 multiplied by 100 is equal to 1,000. And this is what I was talking about, referring to earlier on. When dividing a whole number by a power of 10, the number of zeros in the power of 10 tells us the number of decimal places that the answer will have. 1,000 has 3 zeros. The answer will have 3 places of decimal. Notice that we have the point here 1, 2, 3. How many zeros? 1, 2, 3. One common mistake here could be to put 3 zeros here. 0.0001. That is not correct. That would make the number of decimal places equal to 4. But we know that we need to have 1, 2, 3, 3 zeros, 3 decimal places. Therefore, 0.0, that is 1, 0, that is 2, and 1, that is 3 places of decimal. This is where our fun begins. One of these days, when you jump on your calculator, it will explode from overuse. Let us therefore attempt to solve this part of the problem without its use, without the use of a calculator, just in case the calculator has only one problem left before it blasts up. Right, so we are taking precautionary measures to ensure that we do not use the calculator, because we have been battering the calculator, abusing it, misusing, overusing the calculator to the extent that we do not know. We expect it will blast up anytime now. So good that we do not have to use the calculator in this particular case. We surely need some amount of space for steps, graphics, and explanation. We will therefore use a slide that does not have the script on the left. So next slide, not necessarily the next slide, but the slide that we'll be using to do the division will not have the script on the left. So, no script on the left, in the same way that we have for some others in this presentation. Of course, when we need a lot of space, we do not include the script. And when we will do our division, long division, we will need a lot of space, so no script will be on the left. Isn't that nice? We are not reducing fractions in this problem, although we should be able to. We will use regular division. Therefore, we will do what it takes to remove the decimal places from the divisor alone, and do the same to the dividend. So we will not remove the decimal places from the dividend. We will do what it takes to remove the decimal places from the divisor. And whatever it takes, we will do that same thing to the dividend. The divisor has 2 places of decimal. We will therefore eliminate its 2 places of decimal and increase the dividend by 2 places of decimal also. So in removing from the divisor 2 places of decimal, which is increasing by 2 places of decimal, we will also increase the dividend by 2 places of decimal. Two places of decimal. Let us now eliminate the point from the whole number from 314 and also discarding leading zeros in 005.181. But we cannot eliminate the point here. We are discarding the leading zeros and we are eliminating the point here, since we have a whole number right there. So that is what our problem looks like. Immediately, we will move merrily to the next slide, where we will have some fun with our long division and decimal fractions. Exciting. Set up our division problem as in former years. The good old days when we used to have a lot of fun with long division. First, we say 314 into 5. Not possible. So, we place a 0 over the 5. The answer will not have a whole number part, so we follow the 0 by a point. The fact that when we say 314 into 5, it cannot. Before we can say 314 into 51, we have to bear in mind that there's a notable sign here. Therefore, by going beyond the point, then we know that we have exhausted the whole number position. Therefore, we will not have any whole number because 314 does not divide into 5 anytime at all. So there is our point. Since we are going beyond our point, we have to include that decimal point at that stage. Then what do we say next? 314 into 51. Also not possible. So we place a 0 over that 1. 51, the 0 goes above the 1. Not possible. But surely, finally, 314 can divide into 518 for sure. One good indication of the number of times is the number of times that the first digit can go into the first digit. So this is the first digit, 3. How many times it goes into 5? 1. Right, that is a good indication. So 3 into 5 is 1, so 1 is what we will use. So one good indication of the number of times is the number of times that the first digit can go into the first digit. If it can. Since 3 can go into 5 only once, the answer is quite likely 1. How do we know that it is actually 1? Because 1 times 314 is 314. If we subtract that from 518, the answer that we will get will be less than 314. So 1, what do we do with this 1? We say 1 times 314 is 314, and we subtract it right there. So we then multiply 314 by 1 and take the result from 518. So 314 multiplied by 1, 314, we will subtract that from 518, and the result is 204. It's a fast and direct. 4 from 8 is 4, 1 from 1 is 0, 3 from 5 is 2. Nice. 314 cannot go into 204. If it could, then we would be sure that this should not have been a 1. Maybe a number greater than 1, maybe just 2. But as long as this number that we are using here is correct at this stage, then the number that we will get here, this number should not be able to go into it. So, because it cannot go into 204, we therefore use the 1 that we have there. Now it is 2041. We then say 314 into 2041. A good indication of the answer is the number of times that the first digit can go into 20. So we are saying 314 into 2041. How many times? A good indication of the answer to that question is, we cannot say the number of times that 3 can go into 2 because we know that's not possible already. So we say the number of times that 3 can go into 20. And 3 will go into 20 6 times. So 6. And let's see what happens. 6 times 314 is 1884, which we will take away from 2041. So we go straight ahead saying 6 times 314 turns out to be 1884, and we subtract that from 2041. And what is the answer? Let's see. 4 cannot. 1 from here. 11. 7. Do not forget now that 1 is gone. 3. So we go all the way over here and we push this one down here, 9, and then this one. What is that? A 1. 13. 8 from 13 is 5. So 57 here, and then 8 from 9 is 1. So we should have 157 if my mind is working efficiently. Nice. 157. See, it is not impossible. 314 cannot divide into 157, so we include a 0 from there. Well, actually, there's nothing there, and 0 means nothing, so we can take 0 from there. That's not illegal. A good indication of the number of times that 314 can divide into 1570 is the number of times that 3 can go into 15, because we're sure it cannot go into 1. 3 into 15, how many times? 5. So we say 5. And then when we multiply 5 by 314, the result is 1570, and we will subtract that from 1570. 0. We are done. Very nice. The answer is 0.0165. Right there. Nice. The result is 0 when we finish our last subtraction. This indicates that the answer is a finite decimal and is exactly 0.0165. We will finish up by writing the answer in the forms that are required by the statement of the problem. We will now write the answer correct to 2 decimal places. Locate the second decimal place 2 digits to the right of the decimal point. Now that 0 is important because it is occupying a decimal place. So a significant decimal place, that decimal place contributes to the value to the extent that if it is removed, the value of each one of these digits will be different. So it is significant as a decimal place in that position. So 1, 2 decimal places. Check the digit that is next in order of significance, the one that is located to the right. Is it 5 or more? Yes, it is 5 or more. So the digit is 6, and of course 6 is greater than 5. We add 1 to the 1, which is the digit in the second decimal place. This one. The 1 is greater than or equal to 5. We add 1 here. So that's a 2. And the other digits are not affected and return as they are. 0.02. 2. When rounding numbers, if the digit next in order of significance to the digit in question, so this one is the digit in question, if the one next in order of significance is greater than or equal to 5, then we add 1 to the digit in question. In this particular case, the digit in question is the one in the second decimal place, and the one in the second decimal place is this one. Next, we will write the answer correct to 3 significant figures. Locate the third digit in order of significance by counting from the first non-zero digit from the left. Significant figures from the first non-zero digit from the left. First non-zero is that one. 2, 3. The number only contains 3 digits of significance. Therefore, it is already only written to 3 significant figures, and we do not interfere with it in any way. It goes back exactly as it is, like that. No other digit following the third most significant digit. When rounding numbers, if the digit next in order of significance to the digit in question is less than 5, then we do not add 1 to the digit in question. In this particular case, the digit in question is the one in the third significant position right here, and it is this 5. This one is the digit in question. There's no digit beyond it. There's no other digit to check. Finish up by writing the answer in standard form. That same number written in standard form. The number needs to have 1 non-zero digit to the left of the decimal point. So count the number of places by which the number has to be increased or decreased in order to have 1 non-zero digit to the left of the decimal point. 0, 1, 2. Right there. The number is increased by 2 places of decimal. The number is therefore multiplied by 10 to the power of 2, which is the same as 100. So that is our new number. Has a difference between these two of 2 places of decimal. We need to recover because we multiplied by 100, which is 10 to the power of 2. Now we need to recover the original value of the number by dividing by 100, or 10 to the power of 2. So we divide by 10 to the power of 2, which is the same as multiplying by 10 to the power of negative 2. A number that initially had no non-zero digit to the left of the decimal point is called a small number and will be accompanied by a negative power of 10 in the end. So the sign of the power is playing a very important role here. This being a small number, or classified in our mechanics as a small number. A small number will be accompanied by a negative power of 10 in the end, and the number of decimal places by which this one differs from this one will tell us whether it is 1, 2, or 3, the size of the power. The sign of the power is determined earlier on by calling this small, and small accompanied by negative power, because small number, we say, do not have any non-zero digits to the left of the decimal point. And also we are saying that this differs from this by 2 places of decimal, so there is our 2.